thank you very much for the introduction. Thank you very much for your nice presentation. And that actually the base brain to this presentation, because we all, thanks to the nice presentations, as I said, and there's already a very fundamental important base that why we use the port-based thinking. And now, if we want to use that port-based thinking to do numerics, if we don't develop anything new, what we can do, and we can probably use the existing, for example, the commercial softwares or some open source things. And for the commercial ones, of course, they are like black box, and we just need to know the basic idea of mesh and the finite volume, finite difference. Then we can just link. Then we can do it. And if we use the file drag, then we have to work out all the formulations on paper and carefully do the time discretization, spatial time discretization. Then we pick up the correct spaces there, and we do the numerics there. So we can see that there's a huge gap between the port-based representation and the real simulation. So that's why it brings to this library, and there are some new features I can present from the very beginning. It's that we, of course, use the port-based multiphysics representation, so which enable the Lego-like simulation, which cannot be done. But yeah, there's a similar idea in the common source, but it is not like open source thing. And also, we will use differential forms as the mathematical language rather than in the finite element library like Fadrac and Phoenix. They use a classic vector or tensor calculus mathematical language, and we want to encode from the equation to the weak formulation and the discretization within the library rather than. So we want to do that within the library rather than on the paper. I think this will decrease the risk that you made some typos there and you may have minus plus here and there and around there, which would be a disaster for the simulation. It may take hours, days, weeks to debug a very small typo there. And by doing that with our code, and we can, of course, we don't need to deal with this small typos risk there.
And also, if I can add, but of course, it's not only because of this, but because this then enables, for example, a proper user interface to be directly implemented on something like this. So you can have also something which is checked, and by this is discussion with Twente similar.
Yeah. I will go to that in the next presentation. But so it's called Phyem, and what does it mean? Because it's both Hamiltonian, it's physics, and it's a share in Python, and it's finite element method. So and there's a web page there, but it's just initialized on the web page, and we still need to write a documentation to make that readable, but the website is there. Okay. So basically, this is the idea, and we want to have a library from the port-based thinking to simulation, and because we based on the port idea, then it will be like the simulator. So this is the flow of our Phyem simulation, and a very good representation of the port-based thinking or the port-based modeling is the bound graph, and the bound graph basically is like this, and it is taken from Rami's PhD thesis, and we can say we have this direct structure, we have the storage, and we have the port connected by this. So whenever we want to add new physics to it, we add another indirect structure, and we add port to connect them. So from this port, and so from this bound graph, and we can initialize our simulation. And of course, because we are doing finite element, we are not going to do some discretization on our figure like that. So we have to first introduce our API from this bound graph to BDE. So when we import our bound graph, our bound graph, and of course we need first to have an idea, have a class, how to represent a bound graph with code, but we can do that. And then it's our API from bound graph to PDE. But with a PDE, PDE is just a big class, we need to have the gradient for the PDE. And firstly, of course, at this stage, everything is abstract, and we can have a manifold, abstract manifold. We call it M. It is there, but what the shape of it is, what is metric, what is coordinates, we don't know. And we build a mesh, and we of course we have the function spaces on that, and within a function space, we can have a form. Basically, a form is just one cochain in a space, and which is just a particular instance of a space. Then we use the form as the ingredients for the PDE. And then in the code from the PDE, we go to the wake formulation. They still have this ingredients. And then we go from the wake formulation to algebraic proxy. This is just the discretization, and it has terms. And eventually, from this we have particular implementations. Firstly, we can have a mimetic spectral element implementation in Python, and this could be the first implementation because it will be very unfortunate installation, because if you have a computer, no matter it's Mac, Linux, or Windows, and if you install Python, then you can install the most fundamental, the basic libraries like NumPy and SciPy, and then you can run it. And this is mainly for the education purpose, because when you show this idea to the freshmen, then they can quickly play with it with a very fast installation. But if you want to accelerate your simulation, of course, the Python is quite slow, and you will have new other more and more fundamental, but more faster and faster implementations. But all these are just a particular implementation based on what we have done in an abstract way before. So and so the core of this presentation will be a demo of using this library, but because we don't have a documentation yet, so I have to go step by step to show what we are going to hear. So, okay. What we want to do is to 2D simulation, and we have a dipole here, and it will move to the right with self-induced velocity, and it will has a wake goes to the left, and the four walls are just the solid walls, no slip walls. So if we use the Phyem in Python, it's just a shell in Python, and we import the Phyem as ph, and then we have to do some very preliminary configuration for first. Let's say we are doing 2D simulation, and we use high accuracy. That means when we compute, for example, the mass matrices, we will use overkill or numerical quadrature. But this will decrease the sparsity, but we it's just a option. Then we initialize a manifold. This is the domain we are going to do, but at this stage it's just abstract. We know there's a manifold out there, but we don't know any detail about it. And then we initialize a mesh. What we do next, because normally we do all these things on paper, but now because we do all the things on paper, we want to do it here in the code. So next, with the manifold, and we can initialize some space. This lambda means the scalar valued forms space. We have a zero scalar valued forms, which is out-oriented or pseudo form, and we have zero form space, one form space, two form space, and then with these spaces, they are called out 0, out 1, out 2, and we can make forms in these spaces by doing just the method called make forms, and we can. W is the omega, which is the out vorticity, and then we have UP and velocity and total pressure. Then we can do operator with these forms. Of course, normally these things are done on paper, but now it is with the code, and we have a cross product. And we have exterior derivative, co-differentiation, time derivative, anything, and they are new forms. So, and if we want to look at these forms, we just do ph list all forms, and then we can see all the forms we have, and these are the forms. These are the symbolic representation of the forms, and these are the linguistic representation of the forms. And they are in these spaces. This means outer, and we know they are root forms because they are defined, and all the other forms are derived from the root forms, so they are not root. And by doing this, now what we shall do is we use these forms to build a PDE, which is very, very simple, and we just write the PDE, the expression of the PDE is equal to this. Basically, we can know these are just the names. Okay, why? Yeah, these are just the names of these variables, right? So, and we use this expression to build the PDE, and we set the unknowns of the PDE to be this, and then we can define the boundary condition of the PDE, and on the boundary of the manifold, it is trace of U. And basically, in this sense, it's the normal component of the velocity. And then we, of course, want to we want to have a look at the PDE. Then we can do PR. PR means print representation, and we can see in a vector calculus form or not, or form. So this is the form, and we can see this is the PDE we build, which exactly is the invaded Navier-Stokes equation. And if we do this, we say it's equal to true, and then we can see the vector calculus representation of it. By doing this, because especially in 2D, we will suffer from some minus and plus in the PDE. For example, here we have a minus here, but with vector calculus, it's a plus. So because sometimes the input could be given with this, then we want to make sure if we are coding the correct PDE, and we have to do this to check each other. And this normally is very annoying when we do it on paper, and we have to switch things. Is it 2D or 3D? When it's 0 form, then we have a minus. When it's 1 form, there's no minus. But if we encode this with the library, everything will be shown very easily. Okay, now from the PDE, we can test the PDE with the spaces. Of course, this is a weak formulation. This is a standard way, and what we can do is to do the integration by parts to the third term of the first equation. Basically, it's the fourth term of the first equation, because Python index starts from 0, and because that, we have 2AD, which is the co-differentiation. So we need to do the integration by parts to these two terms, and we will delete this boundary terms because we have no slip boundary conditions. So the boundary integral there will be there anyway, and we can delete this. And then we can get the weak formulation, which is exactly what we do on paper by pen. And then it's temporal discretization. We first initialize an abstract time sequence, and we say, okay, we have this interval from k minus 1 to k, and we have this abstract time instance k minus 1, k minus half for k. What is k? We don't care at this moment, and then we do a note of this thing. Okay, this looks a bit now because we have a lot of terms, but if we can carefully do this and we PR, it means print representation, we get the temporal discretization of this Navier-Stokes equation. As you can see, the boundaries. The boundary condition is well handled, and of course we do the same. It's a special discretization, but this time, no, this is just still the weak formulation. But we just write it out because because for example, we here we use the midpoint discretization, so it will gives us four terms, which are exactly this 4 terms, and this is the temporal discretization. So this will all be done automatically. And what we do is now we give all the spaces a finite degree. It's n. In this case, n is equal to 3, I believe. And NP means matrix proxy, and it's a nonlinear system. So we call the nonlinear system, and we can PR it. PR it means we present the nonlinear system, and eventually it gives like this. So we are solving for k minus half, and these are the known thing, like u at k minus 1, omega at k minus 1, and this is the convection term, and these are the convection term as well, and it will give us a nonlinear term here, which is dependent on this thing, and this is the test function, of course, and still the boundary condition will be there. To this stage, everything is abstract. So we know it is a mass matrix. It is a matrix for the gradient. It is a matrix for the divergence. But what the matrix are, we don't know. That means we have to bring it to a particular implementation. That means we want to use which kind of basis function, which kind of finite elements for it. For example, we use the mimetic spectral elements within a Python environment. We just call this. We call the finite element, apply the mimetic spectral element method, and then we initialize a domain. It is from -1 to 1, -1 to 1, so it's a square. And we initialize a mesh with a mesh layout, and mesh layout is at background is just a list. So this, and if we do this, then we see the mesh, and this is the mesh we are going to use. What is next? And we have the temporal. We make the time sequence be a particular, and we do just, and we initialize a initial condition, and we put the initial condition to the variable, and we reduce it from the continuous level to the discrete level. Then we can visualize the initial condition for the W, which is the vorticity, and we can see something like this. This is the initial condition of omega at t equal to 0, and then everything's ready. We just need to solve it. So we put the boundary condition to the nonlinear system, and for time step is from time step 1 to the end, and within each time step we solve it, and we visualize it, and because at each time step we save the solution of omega, and then we will have a lot of omega pictures. If we make all the pictures in a movie, then it's just the solution is from t equal to 1 is from t equal to 0 to t equal to 1, and solves a nonlinear term. Yes, and the last is the mesh adaptivity, because now when we solve something like this, and this flow is very local, and if we want to get more details, we don't want to refine anywhere. We just want to refine the places where the flow is very complicated. So we do something like this, and if we write the code, and the mesh follow it, and do the rest. Yeah, but by the way, this is still developing. So this is just a demo. So it's kind of cheating, because this is pre-solved, and I use the solution to demonstrate the mesh adaptivity. But this is a very guaranteed result. We already used the mesh, the random a mesh like this to solve all the simple problem. We just need to code it up to solve more complicated thing. But this is a very promising result. Yes. Okay, that's the presentation. Thank you very much.
I'm very, very excited. You see, this is pretty amazing. Arjen.
Yes. Okay. Indeed, very nice. So on your first slide, you were mentioning the console and ANSYS.
Yes.
So do you mean by this that you can also couple this to ANSYS and to a console?
No,
what do you mean by this?
No, I just mean, so if we want to do the simulation now, we currently on the market we have these options. We can use the commercial ones, and they are of course very powerful, way more powerful than mine, but they are like black box, and they are mainly for engineering purpose, but for educational scientific one, we don't know what's going on there. So and this one, they are open source. We know what's going on, but there's a gap. So it's like. Yeah.
And what it says is that you don't know. It's exactly what's happening. If you want to use it for engineering, you just trust, belief that this is telling you anything meaningful. And then, in order to do that, you need to have a very high meshing, to have start from very high definitions, and then you can say, okay, I go and lower. What Rami was saying, you don't know if it's stable. It can get very easily unstable if the mesh is low. You don't know what is under. Instead, with this structure preserving stuff, it is by construction stable.
Sure, but
and this is not what this do.
Practical point of view, there is a lot of software that is based on this.
Sure.
Kinds of industrial things.
Yeah.
And it would be nice if you have a way to couple your very nice library.
Yeah. Because
existing things.
Yeah.
At least partially.
Yeah, because for them, they are commercial ones. They are kind of closed. But but we plan to have API to do them. So the really computational part to solve AX equal to B, we use this one. But when we solve it, we can link to FileDrac to use very fast solver there. So that's something we are going to do.
This is more marketing, right?
Yeah, sure.
No, but it's very important. But I think it's for us. I think it's much more important to have something that's. And the first step would be for us to, because of course this is very fundamental. All symbolic stuff. We are in contact with Twente because what we want to do is, because they are the champions in making user interface and connected the core. Because if that is done, then you have a package which is in any case usable. And then the next step would be, how can you make it interfaceable with other things?
Sure. No. Okay. So I'm just pretending that I'm a practical guy. Which I'm really not.
Any other questions, Mark?
Yeah, I saw in your layout that the starting point is the PDE, and from the PDE you get a weak formulation.
Yes.
In many cases, you start from a functional.
Yes.
And taking variational derivative from a functional, and this gives you the weak formulation.
Yeah.
From which you can deduce what kind of PDE.
Yeah,
so
this is.
You opt for this approach.
This is just the one flow we are coding now. Actually, this actually means the input. We can input from a bound graph, and we can input from a PDE. The demo I show is input from PDE, but because we still need to code this API. But at the time being, we can input from weak formulation, and maybe in the future we code something here is a Lagrange, and then we link to weak formulation. That's something we are going to code.
Because that was Stefano's glue.
No. That's the glue is exactly to have this, to start from a decomposition. So the idea we would like to have is that you have in the library, you want to model a wing flapping in fluid, just to give an example. Then you have an object which is wing, and then you define the shape of the wing, and then you define its property, and then you define a field. Then you have fluid, elasticity, and then you have an actuator, and you build the topology of the bond graph, so to speak. And then you know that domain has certain physical laws, and the interface are compatible, so the Legos pieces can attach together. And then from there, you generate automatically the PD using the theory that we have been developing. So our view is exactly from the top down, so from the bond graphs. Because if you have that from an engineering point of view, that's exactly what you do all the time. It's just that it's done normally in library as finite elements, as a lumped system, the mass, the spring, etc. You touch them, and we will be able to do that, but with PDEs.
Yeah, and if at this time being you have a Lagrangian, then you'd better work out your weak formulation then use it.
So it's really that's the difference between a variational principle driven by Lagrangian way of thinking. The Hamiltonian is very similar, but the Port Hamiltonian is different, because the Port Hamiltonian is not, let's say, kind of related to the Lagrangian. It's like a Legendre relations, kind of our way of. It's conceptually another way of working, because you decompose the things. And the port is what is really the structure. And once you have the port structure, you can do anything. You may have a model which represents a fluid full of particles with electromagnetic properties, and then you have a port which has an electromagnetic features of the field, and you have a port which is a fluid, click, 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 and you work.
For the example of the vortex pair,
Yes.
approaches a wall, I think it is it a wall?
Yes.
I'm used to it that the vortex pair rebounds. So it creates a separation vortex on the wall, and then these two form a dipole, then moves the vortex away from the wall.
Yes.
But in your case, it appears to stick to the wall.
Okay. This part you mean?
Yeah?
Okay, but
And then
I'm not aware of that.
reality, I think they move apart along the wall.
I'm not sure because this is a very standard benchmark. Actually, yeah, this is yeah. We compared with the reference result. This is very accurate. I'm not aware of the phenomenon you are talking. I'm sorry. Yeah, but this is. I'm sure this is very correct from the literature at least. Yeah.
That relates to what happens to a trailing vortex pair of an aircraft
Okay,
when
okay.
it lands. Then this vortex pair comes also very close to the wall,
Uh-huh.
and the vortex rebounds from the wall and moves apart.
Okay.
Say, for example, to the next runway.
Okay.
There it gives a problem.
Okay. Yeah, that sounds.
Maybe it's parametric, the choice of parameters that you chose on.
Maybe add different Reynolds number and we can show
Yeah.
that. Yeah.
You have a very low Reynolds
Oh
number.
yeah, this is just 625. Yeah, this is nominal.
So maybe it got caught up in the viscous boundary on the
Yeah.
wall.
yeah.
Paul?
Yeah, you used a fixed time step.
Oh, in this one, yes, yes.
And is it also possible to use variable
Sure,
step?
sure, sure. It's on the time step. It's just this one. At the first, during the abstract stage, everything is abstract. It's just at time step k, k-1, okay. But now with this command, we specific the time sequence to a particular one. It's a constant one, but we can implement what any kind of one to just to net the code mean t k. It is what tk minus 1. It is what. Then it can do whatever.
It's very, you know, what I like very much in what in this work of Yi is that, you know, if you look SIDOPS, which is the language of Twente sim, it's the kind of same approach, right? You write it down, you write the relations, that's the physics, and then when you do the numerics, that's a different story. This is exactly that dichotomy.
Yes, but if you have a variable step size, you look at the dynamics of the model, right? And how it's doing simulation.
Yeah.
How would you correlate that to the model that you have?
Or in the numerical core.
Yeah,
That's okay. Not in real time. So basically, what Pauli says, you know, here now you specify the time steps, but if you would do it in a kernel in which in real time you change the time, I think it would be very similar to the adaptable mesh.
Yeah. What we can do is to code something like real time sequence, so it will calculate from the solution what is difference from this to the solution. If it is small, then we make the time step longer. If it's huge, then we make it
like the adaptable mesh.
Yes.
Any other question? Let's have a coffee. Thanks a lot to you. Fantastic.